SwayamPrabha. Digital India. Educated India.
Recovery and reuse of sizes, dyes and other chemicals. Lecture number 24. Let us now see that as we saw in the lecture number 23 that how to reduce the pollution load. This lecture is dedicated for the recovery of some of the useful chemicals from the effluent, so that the effluent load becomes less. Recovery and reuse of sizes, dyes and other chemicals from textile effluent is a crucial aspect of sustainable textile production. An overview of some common methods that can be used are biological treatment. Biological processes involve the use of microorganisms to break down organic matter in the effluent. This can include aerobic and anaerobic processes. Bioreactors and constructed wetlands are commonly used for this purpose. Physical treatment. Physical methods such as sedimentation, filtration and membrane processes are used to remove suspended solids and other contaminants from the effluent. This can help in separating dyes and chemicals from the water. So, somehow some methods have been identified to be able to extract some useful compounds from this textile effluent, and those are biological treatment and physical treatment. Further on, even chemical treatment can help to recover some useful compounds. Chemical methods involve the use of coagulants, flocculants and oxidizing agents to precipitate or degrade contaminants in the effluent. Advanced oxidation processes AOPs such as ozonation and UV hydrogen peroxide treatment can be effective for degrading dyes and other organic compounds. Adsorption. Adsorption technique involves the use of activated carbon, zeolite and other adsorbents to capture dyes and chemicals from the effluent. This can be followed by regeneration of the adsorbent for reuse. So, when it is regenerated, there is an automatic recovery of that particular chemical, be it dye or be it heavy metal. Ion exchange. Ion exchange resins can be used to selectively remove specific ions such as heavy metals from the effluent. Regeneration of the resin allows for reuse. Membrane separation. Membrane processes such as reverse osmosis, nanofiltration, ultrafiltration can be used to separate dyes, salts and other contaminants from the water. Concentrated streams can then be treated further for reuse. So, what it means that some of these methods which have been used for mitigation of textile effluent are very useful in recovery of the resource, and then from the recovery somehow the desired chemical, whether it is dye or any salt, can be recovered and reused. Precipitation and crystallization. Precipitation and crystallization techniques can be used to recover dyes and chemicals in a puriformed form from the effluent. This typically involves adjusting pH, temperature and adding specific chemicals to induce precipitation or crystallization. So, it is also possible that one can precipitate out certain chemicals, and then this can be done by pH adjustment, temperature adjustment, and by adding some precipitating agent. Recovery and reuse system: once contaminants are removed or recovered from the effluent, they can often be reused within the textile production process. So, if they can be recovered, definitely after purification or even without purification, they can be reused. This can involve treating recovered chemicals to meet quality standards or adjusting processes to accommodate recycled materials. I will give you an example. Suppose in a dye bath, a lot of dye is still remaining. It need not be even recovered from there. The only thing is, by color spectroscopic method, one can adjust the desired color by dosing lesser amount of dye in the second dye bath and using it, so that the net result gives the same as what was the previous result of dyeing. So, that means the same dye bath could be used, and this we often do while using natural dyes. This should be extended for the use of synthetic dyes also, and it is possible. The only thing is that consciousness in the mind should be there, that the dye bath should not be run into the effluent process, so that it can be reused effectively. Implementing these methods often require a combination of technologies tailored to the specific characteristics of the effluent and the desired quality of the recovered materials. Additionally, regulatory compliance, cost effectiveness, and feasibility are important consideration in the design and operation of effluent treatment and recycling system in the textile industry. See, it is a mindset. It is a mindset what I want to do with the effluent, and if the effluent is rich in any of the chemicals and if the recovery process is feasible, then that is what the mill manufacturer should do, and cost effectiveness can come out of it. But more importantly, the feasibility is most important, whether we can recover or not, whether we can recycle or not, whether we can reuse it or not. Recovery and reuse of sizes, dyes and other chemicals through biological treatment is also possible of textile effluent, and it is an innovative approach to address both environmental and economic concern within the textile industry. Biological treatment processes. Biological treatment processes such as aerobic and anaerobic digestion utilize microorganisms to break down organic pollutants present in the textile effluent. These processes can effectively degrade various dyes, sizes and other chemicals, rendering the effluent less harmful to the environment. So, it is not that only chemical methods or filtration methods can help recovery. Even biological treatment processes, where it can be aerobic or anaerobic, both processes can also be used for the recovery of sizes, dyes, etc. Bioremediation. Bioremediation techniques involve the use of specific microorganisms or plants to degrade or metabolize pollutants. In the case of textile effluent, certain bacteria and fungi have been identified for their ability to break down dyes and other chemicals, transforming them into less harmful substances. Bioaugmentation. Bioaugmentation involves introducing specialized microorganisms into the treatment system to enhance the degradation of specific pollutants. And this we had learned in one of the earlier lectures, that targeted microorganism is introduced into the bioreactor, and then it targets only a specific compound or nature of compound which will be only degraded and not others. This approach can be tailored to target the degradation of particularly dyes and chemicals present in the textile effluent, increasing the efficiency of the treatment process. Phytoremediation. Phytoremediation utilizes plants to absorb, metabolize or accumulate pollutants from soil or water. Certain aquatic plants have been studied for their ability to uptake dyes and other contaminants from the textile effluent, providing a natural and sustainable means of treatment. So, somehow if it can absorb, if it can hold on, then that is a very good option for the removal of the pollution load. Recovery and reuse. This is the main topic of this lecture, where we are emphasizing primarily on how to recover, what are the different methods of recovery, and how to reuse after recovery. After biological treatment, the effluent can undergo further processing to recover valuable materials such as dyes, sizes and other chemicals. Techniques such as filtration, adsorption and precipitation can be employed to isolate and concentrate these compounds for reuse in textile manufacturing processes. This not only reduces the demand for fresh chemicals, but also minimizes the discharge of pollutants in the environment. So, by recovery and reuse, it is not just a term. By using this technology, we are actually reducing the load, which is the main concern of textile effluent, and that is how it not only reduces the demand for fresh chemicals. If suppose a chemical is recovered, I gave you an example of the dye. The dye bath cannot be thrown just like that, because it is very enriched in dye still, and this can be reused by adding or dosing sufficient amount of concentration of dye, so that the initial dye concentration is reached and the dye bath can be used for second time. So, this is the kind of phenomena that we are emphasizing in this lecture related to recovery and reuse. Economic benefit. Obviously, there is a lot of economic benefit, cost saving. Implementing biological treatment and recovery system can significantly make economic benefits for the textile manufacturers. By recovery and reusing chemicals, companies can reduce their raw material cost and minimize expenses associated with wastewater treatment and disposal. Now, I gave you this example of dye bath. Suppose if initially in the dye bath 10 gram of a synthetic dye or a natural dye is added, and only 5 gram is consumed in the first dyeing process. Still there is 5 gram of dye present in the dye bath. So, in the second time only 5 gram will be required to bring to the concentration of 10 gram per liter, and then it is as good as the first dye bath. So, that is the kind of cost saving and material saving that I am emphasizing. By recovery and reusing chemical, companies can reduce their raw material cost and minimize the expenses associated with wastewater treatment and disposal. Additionally, adopting sustainable practices can enhance the brand image of textile companies and attract environmentally conscious consumers. Overall, the biological treatment and recovery of sizes, dyes and other chemicals from textile effluent offer a promising solution to mitigate the environmental impact of the textile manufacturing while simultaneously promoting resource efficiency and cost saving. So, you see, there are two benefits. One, of course, is the cost saving, and then promoting that resource efficiency is also there, recovery and reuse. The recovery and reuse of sizes, dyes and other chemicals through physical treatment of textile is also possible. It involves various techniques aimed at separating, concentrating and purifying these substances from wastewater without relying on chemical reactions. Here are some of the physical methods. Remember, when we started, we learned that there are three major types of processes that need to be followed for reducing the pollution load in textile effluent. One is physical, the second one is chemical and the third one is biological. So, right now we are emphasizing on the physical method. Filtration. Filtration involves passing the effluent through a porous medium to remove suspended solids including sizes, dyes and other chemicals. Different types of filters such as sand filters, activated carbon filters and membrane filters can be used depending on the specific contaminants present in the effluent. Centrifugation. Centrifugation is a process that utilizes centrifugal force to separate particles from a liquid medium in the context of textile effluent treatment. Centrifuge can be employed to separate suspended solids and concentrate sizes, dyes and other chemicals for reuse or further processing. So, this is very simple. By just adapting the centrifugal force, the suspended particles settle down and that settled material is then isolated and reused. Membrane processes. Membrane processes such as ultrafiltration, nanofiltration and reverse osmosis rely on semi-permeable membranes to selectively separate contaminants based on their size and molecular weight. These processes can effectively remove dyes, sizes and other chemicals from textile effluent, producing a purified permeate stream suitable for reuse and discharge. So, membranes, of course, we know that they have different pore sizes depending on whether it is ultrafiltration, whether it is nanofiltration or reverse osmosis. The semi-permeable membrane has different pore sizes. So, it can retain certain size above the pore size and it will permeate the water effluent which has dissolved material. Adsorption. Adsorption involves the attachment of contaminants to the surface of the adsorbent material such as activated carbon or zeolites. Adsorption processes can be used to remove dyes, sizes and other chemicals from textile effluent with the adsorbent material subsequently generated for reuse through desorption techniques. So, in adsorption, it will first go into the pores of the adsorbent material and later on it is dissolved from the adsorbent material and it can be reused. Distillation and evaporation. Distillation and evaporation processes involve heating the effluent to vaporize water and separate volatile contaminants from non-volatile ones. These techniques can be employed to concentrate dyes, sizes and other chemicals present in textile effluent for reuse or disposal. So, even distillation and evaporation type of processes can also be carried out to somehow reduce the water volume by vaporization of water and separate the volatile contaminants from non-volatile ones. Precipitation. Precipitation techniques involve adding chemicals to the effluent to induce the formation of insoluble precipitates, which can then be separated from the liquid phase through sedimentation or filtration. Precipitation can be used to recover certain dyes and chemicals from textile effluent for reuse or safe disposal. So, precipitation of course is a very good technique, and we understand that the material comes out as a solid, but it should be insoluble so that it can actually settle down. Electrocoagulation. Electrocoagulation is a relatively new method, and it is an electrochemical process that destabilizes suspended particles and facilitates their aggregation for removal. This technique can be employed to treat textile effluent and recover sizes, dyes and other chemicals through formation of flocks that can be separated from the liquid phase. By employing physical treatment techniques, textile manufacturers can recover and reuse sizes, dyes and other chemicals from effluent stream, thereby reducing resource consumption, minimizing wastewater discharge and enhancing sustainability of their operations. Additionally, these methods offer economic benefit by reducing the need for fresh chemicals and lowering wastewater treatment costs. So, there are double profits in this. One is that the treatment cost is reduced because most of the contaminant which can be reused and which can be isolated by any of the methods that we described just now are very apt for removal and reuse. So, recovery and reuse of sizes, dyes and other chemicals through chemical treatment of textile effluent involve various processes aimed at separating, purifying and concentrating these substances for reuse in textile manufacturing processes. Here are some common chemical treatment methods: coagulation and flocculation. Coagulation involves the addition of chemicals such as aluminum sulfate, alum or ferric chloride, and time and again we have spoken about this, to the effluent to destabilize colloidal particles and facilitate their aggregation. Flocculation follows coagulation and involves the gentle mixing of the effluent to promote the formation of larger flocks. These flocks can then be separated from the liquid phase through sedimentation or filtration, allowing for recovery of the sizes, dyes and other chemicals. So, it is a well established methodology. First, suspended solids, a coagulant like alum or ferric chloride is added and gently it is mixed, and then it is allowed to settle so that the suspended particle, the colloidal particle, they can all come together and form flocks, and then these flocks become heavy, so they settle down. they can be then separated by filtration process. Precipitation. Precipitation technique involves the addition of chemicals that react with specific contaminants in the effluent to form insoluble precipitates. These precipitates can then be separated from the liquid phase through sedimentation or filtration. Precipitation can be used to recover certain dyes and chemicals from the textile effluent for reuse or safe disposal. Ion exchange. Ion exchange involves the use of resins or other materials that selectively remove specific ions from the effluent through chemical exchange processes. Ion exchange can be employed to recover valuable chemicals or remove harmful ions from the textile effluent, allowing for their reuse or safe disposal. So, ion exchange again can do two things: either it can isolate useful ions or remove harmful ions. Adsorption. Adsorption technique, where zeolite or activated carbon is used, involves the attachment of contaminants to the surface of the adsorbent material, and this we have learned time and again, such as activated carbon and zeolites. Adsorption processes can be used to remove dyes, sizes and other chemicals from textile effluent, with the adsorbent material subsequently regenerated for reuse through desorption techniques. So, just a while ago we understood that adsorption is for removal, desorption is for recovery, and if that can be done effectively, there is a lot of cost saving and there is automatically a lowering of pollution load. Membrane processes. Membrane processes such as reverse osmosis and nanofiltration utilize semi-permeable membranes to selectively separate contaminants based on their size and molecular weight, and this we have learned and understood very well. These processes can effectively remove dyes, sizes and other chemicals from the textile effluent, producing a purified permeate stream suitable for reuse or discharge. So, these membrane technologies are also very effective. Why? Because they remove the unwanted substances, and the stream of the permeate is actually reusable directly, or it can be discharged into water bodies. Now, during this, a lot of emphasis is being given to pH adjustment. pH adjustment involves the addition of acids or bases to the effluent to alter its pH and precipitate certain contaminants. So, again pH has double role to play. One is of course to bring it down to neutrality, there is a kind of an equalization, and the other role is that it helps in precipitation. By adjusting the pH of the effluent, manufacturers can facilitate the recovery of specific compounds like sizes, dyes and other chemicals, which can be further reused in textile production processes. By employing chemical treatment methods, textile manufacturers can recover and reuse sizes, dyes and other chemicals from the effluent stream, thereby reducing resource consumption, minimizing wastewater discharge and enhancing the sustainability of their operations. Additionally, these methods offer economic benefit by reducing the need for fresh chemicals and lowering wastewater treatment cost. So, by doing this, the whole genesis of looking at the recovery and reuse is from the point of view of lowering the cost, lowering the using of or usage of chemicals, fresh chemicals. So, I gave you an example, again I will repeat that example, that how initially 10 gram per liter dye solution was prepared, dyeing of the first batch was carried out. In the dye bath there was only 5 gram per liter remaining, and it was further dosed with only 5 gram now instead of 10 gram, thereby saving 5 gram of dye, and then by redosing with just 5 gram of the dye, it was possible to achieve the same dye depth in the second dye bath. So, that is the kind of economics that it works in terms of fresh chemical usage, less usage of fresh chemical and lowering of wastewater treatment cost. Recovery and reusing sizes, dyes and other chemicals through adsorption of textile effluent is a promising approach for reducing environmental impact and improving resource efficiency in the textile industry. Here is how it typically works. Effluent treatment. Effluent treatment of the textile, which contains various chemicals including dyes and sizing agent, is collected from textile manufacturing processes and treated. Adsorption process. Adsorption is a common method used to remove pollutants from wastewater. In this process, adsorbent material are used to attract and bind the pollutants, allowing for their removal from the water. Now, selection of the adsorbent. This we have studied in the previous few lectures, that can be very challenging but very interesting, because some of the adsorbents have this very unique quality of adsorbing one particular type of material from the textile effluent. Various adsorbent material can be used for this purpose, including activated carbon, zeolite and certain types of clays. The choice of adsorbent depends on factors such as specific pollutants present in the effluent and desired level of treatment. Now, let me also tell you that here we can make a choice whether we want to use activated carbon or we want to use zeolite or we want to use clay, depending on what is that we want to recover. Adsorption mechanism. Adsorption mechanism we have studied in the past, but we will re-look at in terms of recovery and reuse phenomena. Adsorption occurs through physical and or chemical interaction between the adsorbent surface and the pollutants in the effluent. This can involve processes such as ion exchange, surface complexation and van der Waals interactions. Recovery and reuse. Once the pollutant have been adsorbed onto the adsorbent material, they can be recovered through desorption processes. This typically involves washing the adsorbent with a solvent or regenerating agent to release the pollutant from the surface. The recovery chemical can be reused in the textile manufacturing process, reducing the need of fresh inputs and minimizing waste generation. So, that is the whole idea of using adsorbent, because by a simple physical phenomena or even a chemical phenomena like desorption, it can be either dissolved with the help of a solvent or water or even heat. There are several benefits. Recovery and reusing chemical from textile effluent through adsorption offers several benefits. It helps to reduce the environmental impact of textile manufacturing by minimizing the release of pollutants into water bodies. It also improves resource efficiency by enabling the reuse of valuable chemicals, thereby reducing the consumption of raw materials. Additionally, it can help textile manufacturers comply with the environmental regulations and enhance their sustainability credentials. So, there are definitely, if a process is done, it is done with an aim to benefit in some way or the other. And here there are many-fold benefits. There is cost saving, there is material reuse, and more importantly, the textile effluent pollution load is reducing tremendously if these are recovered beforehand. Overall, the recovery and reuse of sizes, dyes and other chemicals through adsorption of textile effluent represent a promising strategy for achieving more sustainable and environmentally friendly textile production practices. Recovery and reusing sizes, dyes and other chemicals through ion exchange of textile effluent. Recovery and reusing sizes, dyes and other chemicals through ion exchange of textile effluent is another effective method for reducing waste and improving resource efficiency. In the textile industry, here is how it generally works. Ion exchange process. We have already understood that in the past lectures, but we will re-look at it from the recovery and reusing aspect. Ion exchange is a chemical process in which ion in a solution are exchanged for ions in a similar charge on a solid insoluble resin. In the context of textile effluent treatment, ion exchange resins are used to selectively remove certain ions, including those associated with dyes and sizing agents. Selection of ion exchange resins. Various types of ion exchange resins are available, each with specific properties and affinities for certain ions. The selection of appropriate resin depends on factors such as composition of the effluent and the target ion for removal. Now, this is crucial. Which ion we want to remove and how much of it is present in the textile effluent. So, based on that, the ion exchange resins are chosen or selected. Ion exchange mechanism. In the ion exchange process, the effluent is passed through a bed of ion exchange resin. The target ions in the effluent are attracted to and exchanged with ions of similar charge on the resin. This results in the removal of the target ions from the effluent and their retention on the resin. Regeneration of resin. Once the ion exchange resin becomes saturated with target ions, it needs to be regenerated to restore its capacity. This is typically achieved by passing a regenerant solution through the resin bed, which displaces the retained ions and restores the resin to its original state. So, there is a little bit of processing that is required, but nevertheless the use of a regenerant solution can give back the resin in its original form and it can be reused, whereas the regenerant can be then used for reuse. Recovery and reuse. The ions removed from the effluent during the ion exchange process can be recovered from the regenerant solution. Depending on the specific ions and chemicals involved, they may be reused directly in the textile manufacturing process or undergo further treatment for reuse or disposal. Benefits. After all, if we are carrying out ion exchange resin or if we are carrying out adsorption, they are bound to have or they should have benefits. Similarly, even ion exchange resins offer many benefits. Recovery and reusing chemicals through ion exchange offer several benefits. It helps in minimizing the discharge of pollutants into environment, thereby reducing the environmental impact of textile manufacturing. It also enables the recovery of valuable chemicals, leading to cost saving and improved resource efficiency. Additionally, ion exchange can be tailored to specific pollutants and effluent compositions, making it a versatile and effective treatment option. In summary, recovery and reusing sizes, dyes and other chemicals through ion exchange of textile effluent is a valuable approach for achieving more sustainable and environmentally friendly textile production practices. That means that all these processes that are undertaken for recovery and reuse have their set of advantages, and that is why they are recommended for practicing. Recovery and reusing of sizes, dyes and other chemicals through membrane separation. We have seen this, that membranes help to separate. Now, how do they work? What is the recovery process is not what we have emphasized earlier. We have only talked about their use and their potential use. So, recovery and reusing sizes, dyes and other chemicals through membrane separation of textile effluent is an innovative method that offers several advantages in terms of efficiency and sustainability. Here is how it generally works. Membrane separation process. Membrane separation process is a physical process that selectively separates components of a fluid based on differences in their size, charge and other properties. In the context of textile effluent treatment, various types of membranes can be used, including microfiltration, ultrafiltration, nanofiltration and reverse osmosis membranes. Selection of the membrane. Now, this is very crucial. The choice of membrane depends on the specific property of the effluent and the target component for recovery. For example, microfiltration and ultrafiltration membranes are suitable for molecules which are larger in size and macromolecules, while nanofiltration and reverse osmosis membranes can remove small molecules and ions only. And this we had discussed earlier, that these are categorized into micro, ultra, nano and reverse osmosis based on the pore size. Membrane separation mechanism. In membrane separation, the effluent is passed through a membrane barrier which selectively allows certain components to pass through while retaining others. The separation occurs based on factors such as molecular size, charge and solubility. Sizes, dyes and other chemicals can be selectively retained or allowed to pass through the membrane based on their molecular size and properties. Concentration and purification. Membrane separation can concentrate the target chemicals by removing water and other unwanted components from the effluent. This allows for the recovery of valuable chemicals in a more concentrated form which simplifies subsequent processing steps and reduces waste. So, once it is removed, automatically the permeate becomes less in load of pollution. Recovery and reuse. The concentrated solution containing sizes, dyes and other chemicals can be further processed to separate and purify the desired components. Depending on the specific chemical involved, techniques such as precipitation, crystallization or solvent extraction may be used for recovery. Once recovered, these chemicals can be reused in the textile manufacturing processes, thereby reducing the need for fresh inputs and minimizing waste generation. So, the bottom line is that whenever these processes or wherever these processes are used, there are only 2 or 3 major points that are kept in mind. One is to reduce the load of using fresh chemicals. The second is to reduce the load in the permeate of the water that is being treated, so that it can be either directly run into the water bodies or may require some more simpler treatment methods. And then over and above, it is the cost saving process. Concentration and recovery. As the effluent passes through the membrane, the target components are concentrated on the retentate side of the membrane, while purified water or permeate is collected on the other side. The concentrated solution containing sizes, dyes and other chemicals can then be further processed to recover and reuse these valuable components. Cleaning and maintenance. That is very crucial because membrane fouling is a major problem caused by the accumulation of particles and contaminants on the membrane surface, and it is a common challenge in membrane separation processes, whether it is ultrafiltration membrane or microfiltration membrane or nanofiltration membrane or reverse osmosis. Membrane fouling is a major issue which needs to be addressed. Regular cleaning and maintenance of the membranes are essential to ensure optimal performance and prolonged membrane lifespan. Benefits. Now, let us look at the benefits from the recovery point of view. Membrane separation offers several benefits for recovery and reusing chemicals from textile effluent. It provides a selective and efficient method for separating target components, leading to high purity and recovery yields. Additionally, membrane processes can be integrated into existing wastewater treatment system, making them relatively easy to implement in textile manufacturing facilities. Moreover, by recovery and reusing chemicals, membrane separation helps to reduce the environmental impact of textile production and improve resource efficiency. So, what it means that membrane processes are very good. There are lots of benefit. The only drawback is the membrane fouling, which can be overcome by cleaning periodically and maintaining it. In summary, recovery and reusing of sizes, dyes and other chemicals through membrane separation of textile effluent is a promising approach that contributes to more sustainable and environmentally friendly textile manufacturing practices. Then let us look at the recovery and reusing of sizes, dyes and other chemicals through precipitation method. Recovery and reusing of sizes with using precipitation and crystallization of textile effluent is another viable method for reducing waste and improving resource utilization in the textile industry. Here is how it generally works, because we have seen that it works. But how does it benefit from the recovery and reuse point of view? Precipitation involves the formation of insoluble solids from a solution through chemical reaction. In the context of textile effluent treatment, specific reagents or conditions can be used to induce the precipitation of target chemicals such as dyes and sizing agents from the effluent. Chemical selection. The selection of precipitate or precipitation reagents depends on the chemical composition of the effluent and the target components for recovery. Commonly used precipitation agents include metal salts, acid, bases and complexing agents which react with the iron present in the effluent to form insoluble precipitates. So, one has to make proper chemical selection, and that is very crucial in the precipitation step. You cannot precipitate anything and everything with anything and everything. So, the matching of the proper precipitating agent to remove a specific component has to match, and that is what is very crucial. Crystallization process. Crystallization is a method for separating dissolved solids from a solution by inducing the formation of crystals. In the context of textile effluent treatment, crystallization can be used to recover pure chemicals such as dyes and sizing agents from the concentrated effluent solution obtained after precipitation. Controlled condition, precipitation and crystallization processes are typically conducted under controlled conditions of temperature, pH and agitation to optimize the yield and purity of the recovered chemicals. Sometimes some scratching also needs to be done. By adjusting these parameters, manufacturers can tailor the process to achieve the desired outcome. Separation and recovery. Once the precipitates or crystals have formed, they can be separated from the remaining liquid phase using filtration or centrifugation. The recovered solid can then be washed, dried and further processed to obtain pure chemicals. The recovered solid can then be washed, dried and further processed to obtain pure chemicals suitable for reuse in textile manufacturing processes. What are the benefits associated with precipitation methods? Recovery and reusing chemicals through precipitation and crystallization offer several benefits. These methods enable the selective recovery of specific components from the effluent. So, they are very specific, leading to reduced waste generation and improved resource efficiency. Additionally, precipitation and crystallization can be relatively simple, cost-effective processes, making them attractive option for textile manufacturers looking to adopt sustainable practices. So, it is within sustainable practices that these are incorporated. In summary, recovery and reusing sizes, dyes and other chemicals through precipitation and crystallization of textile effluent is a promising approach for achieving sustainability goals in the textile industry. By implementing these methods, manufacturers can minimize waste generation, conserve resources and reduce their environmental impact. Which chemicals can be recovered? Dyes, sizing agents and some other chemicals can be recovered. Several chemicals can be potentially recovered from textile, but not all of them. So, let us look at it one by one. Dyes are one of the most significant components of textile, and I gave you an example also. Recovering dyes from effluent can involve various methods such as adsorption, ion exchange, precipitation, crystallization, or even if it is not recovered, I told you another alternative. Sizing agent. Sizing agents are substances applied to yarn or fabric to improve their strength, smoothness and resistance to abrasion during weaving or knitting. Common sizing agents like starches, polyvinyl alcohol and synthetic polymers are used. These agents can be recovered through methods such as precipitation and filtration. Surfactants can be recovered, are used in textile processing for tasks such as wetting, emulsification and detergent action, and they can also be recovered through adsorption or membrane filtration. Finishing agent. Finishing agents are applied to fabric to impart specific properties such as softness, water repellency or flame resistance. Common finishing agents include silicones, fluorocarbons and flame retardants. These agents also can be recovered through extraction and filtration. Auxiliary chemicals. Various auxiliary chemicals are used in textile and they can be also recovered by pH adjustment, and therefore, acid, alkalis, oxidizing agents and antimicrobial agents can be recovered by precipitation or ion exchange or other separation techniques. Solvents and organic compounds and inorganic compounds also like sodium chloride, sodium sulphate, calcium carbonate are commonly found and they can also be recovered by processes such as evaporation, crystallization or ion exchange. Solvents like for example, alcohol, ketone, aromatic hydrocarbons can be recovered by distillation, adsorption or other purification methods. So, by recovery and reusing of these chemicals from textile effluent, manufacturers can reduce waste generation, minimize environmental pollution and improve resource efficiency in the textile industry. Best methods to recover, of course, let us consolidate, are adsorption and membrane filtration. Best methods of recovery, there are several methods. Now, out of those several methods, which is the best method? So, it is recommended that some of the commonly used methods for recovery of dyes and surfactants from the effluent are adsorption and membrane filtration. Undoubtedly, adsorption is one of the very versatile method of removal of dyes and surfactants. Similarly, membrane filtration, depending on the molecular size of the dye molecule and the surfactant, it can be designed whether ultrafiltration is used or microfiltration is used or nanofiltration is used or reverse osmosis is used. Precipitation is also one of the methods which are categorized under best method. Solvent extraction is another very unique method which we did not discuss much in detail, is used selectively to extract dyes and surfactants with the help of an organic solvent. After extraction, the solvent phase containing the dye and surfactant can be separated and aqueous phase can be recovered from the solvent. Ion exchange, we have spoken much in detail, is also one of the best methods of separation of and recovery of dyes and surfactant. So, we have come to understand that all these methods are recommended for use for recovery and reuse. So, to conclude, in conclusion, the recovery of dyes, surfactant and other chemicals such as sizes from textile effluent is a critical aspect of sustainable textile manufacturing practices. By implementing effective recovery method, textile manufacturers can minimize waste generation, reduce environmental pollution and improve resource efficiency. Ultimately, the recovery of dyes, surfactants, sizes from the textile effluent contribute to a more sustainable and environmentally friendly textile industry, aligning with the global efforts to promote circular economy principles and reduce the environmental footprint of manufacturing processes. So, it is still not so bad. There are loads, but the loads can be removed and reduced. So, with this we have come to an end of this lecture. Thank you.